Hey everyone, and warm welcome to this webinar. We're happy to have you here today to learn more about TurboCollector and how GHEtool can be used to design geothermal systems. My name is Daniel Almgren, and I'm the CPO at the Muovitech Group. With me today, I have my colleague Kim Johansson. He is the CEO of Muovitech Sweden. And then we also are very happy to have our guest, Wouter Per from GHEtool, to talk a little bit about his software. So the plan for today is that I will start with a short introduction of Muovitech, and then Kim will jump into the technical of the TurboCollector. And after that, we will hand over to Wouter, where he will have a company introduction and also the modeling with the TurboCollector. After Wouter's part, we will move on to something I think you will find really useful. We will demonstrate live how the GHEtool software works with the TurboCollector, so you can like actually see how it works in practice. And finally, we will wrap up with a Q&A. So feel free to just drop questions in the chat during the time. And then we will see how much time we will have in the end, and we will try to answer as much as possible in the end of this session. So a few words about us. Muovitech was founded in 2002 here in Bramhult, Sweden. At that time, we were a small company, as many other companies are in the beginning, but we had a really clear vision. Over the two decades, we have grown steadily, and today, as you can see on the map in the picture, we are present in 7 European countries, but we also delivered further worldwide, for example, to Australia and some other countries. We see ourselves as a complete supplier for the geothermal energy systems, meaning we provide everything needed outside the building, which then includes probes, manifold chamber, pipes, and different kind of accessories. So more or less all the components that it's needed to make the system work underground, we can say. From the very beginning, our main priorities has been sustainability, energy efficiency, and innovation. We believe that these three are essential for the future of geoenergy. And one good example for that is our TurboCollector. It's already been installed in more than 100,000 systems, making it a pretty well-known solution on the market already. And with that introduction, I will hand over to my colleague Kim, who will tell you a little bit more about our product, TurboCollector.
Yes, thank you, Daniel. I will just get the presentation started. Like Daniel described, Muovitech has been in the business for more than 2 decades, and one of our slogans that I think we have used all the time from the beginning is best in earth. And the plan is that our products will end up in the earth. Except for this slogan, we have another one that is turbulence is the heat pump's best friend. And this is the core of this presentation, I would say. We would like to try to explain why we think turbulence in the brine is important and how it could make the heat pump systems more efficient. But first, I will talk a little bit about the challenge or the the problem that we are trying to solve with this product. And in the top left, you could see one graph where we are describing the borehole resistance in comparison to the flow rate or the Reynolds number. And if we are starting from the bottom, we have this yellow field, which we refer to as grout. And above that, we have a gray field that we refer to as pipe. And these two are the resistances for the grout and pipe, of course. But what's interesting to see in the graph is that these two resistances are constant. So if we increase the flow rate or the Reynolds number, we can't affect the borehole resistance in these two sections. Above that, we have a red field, which we call fluid, and this is the resistance within the brine. And the first thing that we could see is that it's quite a large resistance, but we can also see that it's not consistent. So if we increase the flow rate and increasing the Reynolds number, eventually we will come to a point where this resistance will start to decrease. And eventually it will be a very small resistance. And what's happening here is that we are going from a laminar state in the fluid to a more turbulent state. And this affects the combined borehole resistance a lot. On the bottom left, we are trying to explain a little bit what is the difference between a laminar flow and a turbulent flow. And in a laminar flow, we have all layers in the fluid moving in the same direction. It's moving in the same direction as the pipe. But the layers or the molecules closer to the borehole wall, the pipe wall, of course, is moving slower compared to the fluid in the middle of the pipe. And this has to do to the resistance of the friction against the pipe wall. If we increase the flow rate enough, these layers are starting to break up and we have a much more turbulent flow. And that means that we will have a better heat transfer and a more convective heat transfer. Our product that we are talking about today is the TurboCollector. And we are trying to affect this turbulence using this pipe. And basically, it's a normal polyethylene pipe with the addition of these fins that you could see in the picture. And these fins are rotating back and forth in the pipe. And I will come back to that a little bit later, why it's important that they have this twisting. The idea with the TurboCollector is that we could create a better turbulence using a lower flow rate. So you don't need as much speed on the fluid to have the fluid turbulent. And recently, we made a study together with a university in Sweden called Chalmers. And in this study, we quite clearly could see what the benefits with these fins are and when they occur. So in the picture on the bottom right, you could see one example of this study. Here we have a cross-section of two pipes, one smooth pipe and one TurboCollector. And the cross-section is done with a Reynolds number of 2050. So normally we are considering the transition from laminar to turbulent fluids occurring at 2300. So this is a laminar state in a smooth pipe. And this is also what we could see in the cross-section. You could clearly see these layers in the temperature field of the fluid. But if we take a look at the TurboCollector instead, we could see that the temperature is much more evenly distributed. And this is showing that we have a more turbulent flow and therefore also better heat transfer. So how does this work? We're going back to the graph that we showed in the first slide, where we could see that we need about 2,300 of Reynolds number before we have this transition from laminar to a more turbulent flow rate. But if we instead were to use the TurboCollector, we could push this starting point back, and we could push it all the way back to Reynolds number of 1,800. And that means that we could reduce the flow rate with as much as 22% and still not end up in a laminar flow. And if we are able to go from a laminar state into a turbulent state, we could actually reduce the thermal resistance in the fluid with as much as 80%. And if we are able to do that, this will have an effect on the temperature that we are getting up to the heat pump. We could have less temperature difference between the ground and the fluid. And as an example here, we have taken an example where we have a probe with a flow rate of 0.4 liters per second using ethanol. So we have, or maybe it was MPG, I don't remember. Anyway, in this system, we have a Reynolds number of 2,000. So with a smooth pipe, it would be a laminar flow rate. And we also have a heat transfer rate from the ground of 50 watts per meter of the borehole. And in this case, the reduced borehole resistance would increase the temperature of the brine with as much as 3.6 degrees, which is a lot. And that will improve the overall COP of the system with as much as about 11%. So if we summarize this a bit, the TurboCollector creates more turbulent flows at significantly lower flow rates, and it increases the COP of the system. And increasing the COP of the system, of course, gives the benefit to the customer that they could save on their electricity. And one really good thing to have this saving of electricity using a different probe is that these are meant to last for a very long time. The lifetime expectancy of this polyethylene pipe is between 50 and 100 years. And if you compare that to the lifetime expectancy of the heat pump, we could quite fast realize that during these 50 to 100 years, you have changed your heat pump several times. The TurboCollector is a certified product. In the Nordic countries, we have one certificate called P marking, and in the rest of Europe, we are mostly using a certificate called ESCOCET. It's also available in all relevant dimension, starting from 25 millimeter up to 55 millimeters. And it's also available in a product that we are calling Muovitech. And in the Muovitech version, you could also go up to 63 millimeters. Muovitech is, as it sounds, a little bit elliptic collector that we hope we could present to you further on. And of course, the idea with the TurboCollector is to maximize the heat transfer in the system. When we are designing geothermal systems, we normally tend to look at the peak load, because this is what's determining how much we need to drill, basically. But one benefit with the TurboCollector is also that it improves the performance in the part loads. We went to a Swedish heat pump manufacturer to discuss this and would like to get a better idea of how much of the year are systems normally working at peak load. And we got this graph that you could see here as a good example. And on the y-axis, we could see the kilowatts used by the system. And on the x-axis, we have the numbers of hours per year. We could quite clearly see that it's a very small part of the year where we are operating at peak load. And quite quickly, we end up in a part load. And the modern heat pumps normally regulates the circulation pump when we are not in peak load. So when the system is not working for 100%, the circulation pump slows down a bit, and then we risk having a more laminar flow, which lowers the temperature of the turbine. But by using the TurboCollector, we could increase this window where we have a good heat transfer, even in part loads. The study that we have made together with the Chalmers University, in that study, we mainly focused on two things. One of the things that we focused on was the friction factor. We would like to see how these fins affect the friction factor, and therefore also the pressure drop. And the second thing that we were looking for was the Nusselt number. And the Nusselt number tells us something about the heat transfer in the pipe. I know that Wouter will talk a little bit more about that later in the webinar. But one thing that was very nice to see in the study of the friction factor was that we are not creating any additional pressure drop outside of this window that we are creating. So when we are in a turbulent state with a smooth pipe, we are not increasing any pressure drop with the TurboCollector. In this study, we actually made more than 30 different simulations. And one thing that we looked at was how these fins should rotate. And we came up with that the design where it twists back and forth was the best. We also simulated the designs where it only twisted in one direction. And that had some slightly better results than a completely smooth pipe, but it quickly became laminar at quite high Reynolds number. And the reason for this is that when the fluid goes through this pipe with the fins in one direction, eventually the fluid would start to follow the fins, but in a laminar state. So what you need is something that quickly abrupts this flow and breaking up these laminar layers. We also tested completely straight fins and saw that we had no benefit whatsoever with this design in the bottom. It behaved exactly like a smooth pipe. And this proves that the design that we have chosen is the most optimal. The full report from this study is available on our webpage. We have also been accepted to have an article in the heat pump conference in Vienna next year. And we will also have an article in a scientific journal called International Journal of Heat and Mass Transfer, where we have some minor revisions to correct before it could be published. Thank you. And now I will hand over the presentation to Wouter.
Thank you, Kim, for this presentation. Now, before talking about the modeling of the TurboCollector in GHEtool, I just wanted to say a couple of words about our software for the people who are not yet familiar with it. So GHEtool was originally founded during my master thesis in 2019 at the KU Leuven in cooperation with Boreholes Engineering, which is now part of the Sweco group. In the summer of 2023, we released the first commercial version to see whether or not there was any demand for another bore field simulation tool. It seems like there was, and in November 2024, we released the cloud version of the software, which is now available online. At the moment, since 2024, we have more than 50 licensed users, more than 350 people trying the software at the moment. We're at the moment also market leader in Belgium, and we're already used in more than 6 European countries. And the goal of next year is then also really the push towards more internationalization. Now, you might be asking yourself, there are other softwares on the market already quite some time, so why do people change to GHEtool? And when we asked our users that, there were 3 reasons which can be summarized that GHEtool is a tool for 2025. We are a catalyst for innovation, and we want you to design with confidence. So what we mean by a tool for 2025 is that we use the most accurate models. So we have regular updates. The last one is actually from this week, more than 50 updates every year. So sometimes with small improvements, sometimes with big improvements, but such that you can always work with the most accurate scientific models. We tend to create a very easy to use interface, but really powerful. So scenario analysis, automated reporting makes your life really easy. And with methods that also help you to design products until 2025. And geothermal systems are not the same as 20 years before. Pressure drop has become more important. Hybrid systems combining air source heat pumps and ground source heat pumps. Our designs became custom. We have tilted boreholes, etc., etc. So this is all feasible within GHEtool. Next to that, we also understand that we cannot change the industry alone. We're just software, so we work together with industry partners, people who have developed innovative products like Muovitech and other manufacturers, heat pump manufacturers, people who came up with other types of antifreeze. We try to create models for their solutions and implement it in the software so that designers can actually design with it. We also work together rather closely with different universities to develop new scientific models and better methods to come up with even better designs. And next to software, we also want to be a partner in training, because you can have a tool, but if you don't know how to use it, it's also not the very useful. So this is a print screen from our YouTube channel. We have more than 10 hours of content on it. We also have our own knowledge base with over 300 pages of articles related to the physics of bore fields, to products, to tutorials, to exercises. And it's actually the biggest source of information on how to design bore fields in the world as of today. And lastly, we also want to be a reachable partner, so we try to be present at as many events as possible to talk to your users and to learn about your experiences and how we can make our software even better. And that's why I also want to end with this slide, this brief company presentation, because we really see ourselves as a community of users, manufacturers, universities, all working together, striving towards better geothermal design. So if you want and if you're ready for it, you can also become part of this GHEtool community and level up your own design game. So that's about the software itself. And now I want to spend some time talking about how we took the study from the university and converted it into a model which you can actually use and design with. First, some things about the modeling of turbulence, because it's a word we all use, but it's really difficult to model it. And it's all around in engineering applications, from chemical pipe simulations to plane wings to the aerodynamics of Formula 1 cars. And the way we model it is by using something which is called computational fluid dynamics. Now, this CFD is needed because modeling turbulence is hard, and that's because turbulence occurs at different time and spatial scales. If you take, for example, a look at the clouds, it's cloudy in Belgium at the moment. This is a turbulent behavior, but it's at a very big scale. But on the other hand, if you open up your tap water at home, the turbulence there is it's much faster and it's at a very small scale. So this makes turbulence really hard to model, and there are three different ways one can do that, which is RANS, LES, and DNS. And it's best shown by the figures here on the right. So RANS is the most fast way of modeling turbulence because it takes away all the small details, let's say. It really focuses on the macroscopic influences of turbulence, and it smooths out everything else, which is why you see really no turbulence at all. It just all smoothed out. A more new model is called LES. It's large eddy simulations, and they make a distinction between turbulence at a large scale and at a smaller scale. So you can see here already some turbulence, and you see this big wavy shape, let's say. So that's is modeled in detail, but then all the smaller turbulence is, again, like the RANS model, very smoothed out. And when the university was trying to model a TurboCollector, we really needed to go into the smaller spatial scales. So that's why they needed something which is called DNS. It's direct numerical simulation. It's very, very computationally intensive, very complicated as well. But it's the only way to model really the small turbulence effect in order to come up with an accurate model of how the TurboCollector behaves. So the model in GHEtool is based on the work of Hitman, which will be published in the near future. It's a DNS simulation for both pipes with internal fins, like the TurboCollector, and with smooth pipes, to have a comparison on how both systems behave. And the way this study was set up is they started with high enough flow rates, so both pipes, the smooth and the TurboCollector, were both turbulent, and then they lowered step by step the flow rates until we find where the turbulence actually starts. And then based on this, we can come up with the friction factor, which is important for the pressure drop and the hydraulic behavior of the system, and also the Nusselt number, which is important for the heat transfer and the borehole effective thermal resistance. And then there was some sensitivity analysis Kim already touched upon on the number of fin, the fin height, etc. Now, if we look at the simulation they did, we have a smooth pipe here on the left. We see with a Reynolds number of 3,300, there is very good mixing. It's all turbulent up to 2,300. And then somewhere it becomes laminar really fast. So when it's 2050, we see that it's clearly laminar. You see clearly this temperature gradient in the pipe. When they did the same for pipes with fins in it, we see that when it's 3,300, we're turbulent, and we stay turbulent until somewhere around 1,800. You already see here a very, very small but unstable laminar layer. So it stays turbulent way longer. And based on this simulation, they actually found this very complicated graphs, but let me just go through it. So what you see here is on the Reynolds number, x-axis, you see the friction factor, and we have this blue line and this green line. And these are just correlations we have known for decades. And it's basically a reference, whether our model worked or not. The black dots are regular smooth pipes, which, as you can see, beautifully follow these already known solutions. And then we have this red icons, which are the TurboCollector simulations. And as you can see, around 1800, the friction factor increases and the pressure drop hence also increases until 2300, when it was already turbulent, and then it follows again this line. The Nusselt number is important for the thermal behavior. I will not go too much in detail, but here you can see basically the same. We have a Nusselt number for a smooth pipe, and then it jumps to a turbulence behavior. But the TurboCollector already goes to this better Nusselt numbers at a lower flow rate, again showing that there is an improved heat transfer at these lower Reynolds numbers. And this can be shown in graphs for the effective borehole thermal resistance. So just to summarize, the effective borehole thermal resistance tells you something of how easy it is to exchange heat with the ground, and the lower the better. So if you, for example, take a look at this double U shape, you see we are laminar, and then at one moment in time, the flow becomes turbulent and the effective resistance drops off. Now, when we have a TurboCollector, this effect occurs already sooner. So we have indeed what Kim called this window of opportunity. And the same you see with the single U-tube, but there the shape and the size of the window is different because we now have only one pipe instead of two. And if you then take a look at the pressure drop, because the question is, okay, these fins, do they cause extra pressure drop? And yes, they do, but only in this small window. So you can basically say we go from a laminar to a turbulent flow sooner at a low Reynolds number. And the price we have to pay for that is that we also have the pressure drop related to a turbulent flow. So as you can see in this range where the smooth pipes are still laminar, we indeed have a slight increase of turbulence, of pressure drop, because we are turbulent. But in the zone that was already turbulent and the zone that still is laminar, there is no increase in pressure drop. Which might sound a little bit strange because we added fins, and that was also something which was studied in this article, is where they say, okay, if we have a fin height of 0, there is no difference with the smooth pipe. And when we increase the fin heights, you see that the friction factor at one moment in time, it starts increasing dramatically. So the pressure drop increases also dramatically, but with very small fin sizes, there was actually only an improved thermal side, but not so much a worse hydraulic behavior, which is exactly where the TurboCollector, the product itself, was designed. So this was, in a nutshell, a summary of the article by Nicholas Hittman, and I give the floor back to Daniel or Kim. I do not know who is going to continue, but to show you how you can design it actually in GHEtool.
Perfect. Thanks, Wouter. I will share my screen again and go into GHEtool Cloud. What we have made here is basically two different scenarios, or one example, but we're looking at two different things. I must say that the GHEtool is quite easy to use for a new user. It's quite straightforward, and we will go through the examples that we have made. And the first thing we need to decide is what is the aim of the simulation. And here we could choose some different alternatives. What we will focus on today is the option that we could calculate the required depth. And we will also take a look at the temperature profile of our calculation. So first, under the general settings, we need to make some limits to the simulation. And the first thing we do is to determine what is the minimum average fluid that we could tolerate. And in these scenarios, we have put that as 0. And we have put the maximum allowed temperature fluid temperature to 18. And we will simulate a period of 20 years. Then we have another option here, which I think is quite clever, and that is if we want to have temperature-dependent fluid properties. And this we have clicked in yes. So basically what this means is that when the temperature is changing in the system, it also affects the properties on the fluid, and the software takes this into account. We also have the option to include the hydraulic design and to have a result of the pressure drop. And this we have clicked in yes, but we have not chosen to include any header pipe. And the reason for that is if we were to do a real simulation for a real project, I would have included this. But in these examples that we would like to show, it doesn't bring any value. Then we go to the next option here, which is ground. And here we could put in data for the soil or the rock that we are drilling in. Here we have put in some data that we have a thermal conductivity of the soil of 2 watt per meter Kelvin, and we have decided that we are drilling in the Amsterdam region. We go forward to the borehole field, and here we have decided that we will have 2 rows of boreholes with 5 boreholes each. So we will drill a total of 10 boreholes, and we will have a spacing of 7 meters, both in length and width between them. And of course, the borehole diameter is also something that we could choose here. And in this example, we have chosen 140 millimeter boreholes. And then we jump into the borehole resistance. And here you have 2 options. Either you could calculate or let the software calculate the borehole resistance for you, or if you have made an TRT, then you have a measured value that you could put in. Then we decide what type of probe we are using. And in the first scenario here, we will use a smooth pipe with 32 millimeter, and we will use a double loop system. So 4 pipes going into the ground, as we could see here, in dimension 32. And the fluid in these pipes will be monopropylene glycol, and we're using 25% in the boreholes. We could also put in here the flow rate that we have in the system. And in this case, we have chosen to have a flow rate of 3.1 liters per second. that's going to be divided in these boreholes. Moving on to the thermal demand. Here we have some options if we are putting in the load of the building or the geothermal side. If we would like to use or include domestic hot water or not, and in this case we have chosen yes. We could also choose a little bit on the peak duration of heating and cooling. And in this case, we have decided that we will have a maximum effect of 60 kilowatt in this scenario, and 100,000 kilowatt hours of heating, that is. And then we have also added 25 kilowatt of cooling and 17,500 kilowatt hours of that. And here we could also put in some data for the SCOP. Then in the bottom here, we could press go to results, and the software will make the calculations. Now we have already prepared this, so I will just press up here to results. And then we have a lot of useful information. First of all, we could include this into a report, so that if you have any clients or so that would like this as a report, we could use that. But already in this view, we have a lot of information. First of all, we could see that we have an imbalance in the system. And this is, of course, because we have more heat extraction than we are using the cooling mode. The next thing we could see is that the minimum average fluid temperature is 0. And this is what we put in as a limit when we calculated the required depth. And the required depth is shown here. So we need to drill each borehole to just above 177 meters to meet the thermal demand of the building. We can also see some information about what state the fluid is in. So for the extracting mode, when we are extracting heat from the boreholes, we could see that the fluid in the pipes is in a laminar state, and it has a Reynolds number of 1,300 approximately. But in the cooling mode, we actually have a more turbulent fluid. So it's a transient zone where we are above the 2,300. Moving on down, we could see the temperature profiles during these 20 years that we are simulating. And we could see that in the extraction phase of heat extraction, we could see that it levels out at 0 degrees, just like we intended. We also have some information about the pressure drop, and we could see that in this system, we have a pressure drop of about 29 kilopascal. I think this is a good example. We were trying to make an example that says something to different persons working in different areas in Europe. And I know that in many countries this double loop 32 is used a lot. The next thing we did was that we copied or duplicated all of these settings and did the same calculation using a single loop 40 instead. And the first simulation, we used a smooth pipe. So all the settings are the same, and we could go directly to the results and see how it differs. First of all, we still have the same imbalance because this is due to the thermal demand. The minimum temperature fluid is the same because we ask the system to calculate the required depth. But here we're starting to see some really big differences. Instead of drilling each borehole 177 meters, the system tells us that we need to drill almost 197 meters. So we need to drill more just because we are choosing a different probe. Going down a bit and looking at the Reynolds number, we could see that in the extraction phase, the Reynolds number is higher, but we are still beneath the 2300. So we are still in a laminar phase. And when looking at the pressure drop, we could see that the pressure drop is slightly less, but in the same region, we have a pressure drop of 26.35. So the next thing we did was to duplicate the scenario again, but this time we changed the smooth 40 millimeter probes into the turbo 40 millimeter probes instead. And here it gets really interesting, I think. If we look at the results for the TurboCollector, we could see that the temperatures are the same, but the required depth is only just above 170 meters. So this is way lower than the smooth solution, but it's also less than the W system using the 32 millimeter pipes. And the reason for that is if we go down and look into the Reynolds numbers, we could see that these are the same Reynolds numbers, more or less, that we had in the smooth scenario, smooth 40. But because we are using the TurboCollector with these internal fins, it becomes more turbulent, as it's described here as transient. And this gives us a much better heat transfer, which allows us to use less borehole meters. And having a quick look at the pressure drop, as Wouter explained before, we have a slightly higher pressure drop within this window, but it's still, I would say, in the same region. Here we have a pressure drop in the system of 32.2 kilopascal, which I think it's very acceptable. So this is one way of showing the benefit with the TurboCollector and the fins inside of the pipe. Another way to look at it is if we go back to the first page, the general settings, and instead of looking at the required depth, we could choose to calculate temperature profile. So once again, we duplicated all the settings and choose the single loop 40 millimeter probe. The only difference is now that we are not allowing the system to calculate the required depth. We need to put in a value for it. So here on the borehole field, we ask the system that it should drill each borehole 190 meters. After that, we could ask the software to run the simulation, and we got these results again. So what differs this time when we are not looking at the required depth is that the temperature fluid will be a bit different. So instead of 0 degrees here, which we put as a limit in the former examples, the software is now allowed to go below 0. So the minimum temperature in this case would be minus 0.6 degrees almost. And once again, we could see that we have a laminar phase, laminar flow rate in the heat extraction. And the pressure drop is the same as in the last scenario, since we have the same flow rate. If we take a look on how this would change if we were to use a TurboCollector instead of a smooth collector, the first thing that we could see is that it affects the temperatures, the minimum temperatures quite a lot. Instead of having minus 0.6, we are now having 1.5 degrees plus. So basically, we have a temperature difference of 2 degrees here that we could that will improve the system. And we could also see that this has to do with, of course, that in this Reynolds number, we again have a transient flow rate, which improves the heat transfer. And again, the pressure drop is really reasonable with 32.2 kilopascal. This was the examples that we had for the simulations. I hope you find them interesting. And I know that there is a free trial using GHEtool. But if you send an email that you have been to this webinar, you would have an additional 2 weeks trial period. So it's a total of 4 weeks instead.
As a thank you for attending to this webinar, you can register to GHEtool and you will get some extra days for the trial version. Please just reach out to Wouter after registration and he will fix this for you. And also further collaboration between Muovitech and GHEtool will be to look into the Muovitech product. But yeah, let's to be continued.